Hey guys, welcome back. This is section 1.5, functions and logarithms. Section 1.5 of 6. So you've almost made it. Congratulations. Good job on all of your hard work to get you this far. Here in section 1.5, this is what we're going to be talking about. We're going to identify what makes functions one-to-one. We are going to determine the algebraic representation and the graphical representation of a function and its inverse if it has one. We're going to use parametric equations to graph inverse functions, and we're going to apply the properties of logarithms. Okay, so first thing, one-to-one. Hopefully you remember. This is what one-to-one means. First off, this is a fairly mathy definition. It says f of x has a domain where f of a is not equal to f of b whenever a is not equal to b. Well, more simply put, that means no two different values of x map onto the same f of x. Or, even more simply, the graph of f of x would pass the horizontal line test. So let's take a look graphically. First we have our cubic function, y is equal to x cubed. Let's the horizontal line test. Anywhere we were to put a horizontal line, you can see I have it going right through here, but any place I might move this up or down, that horizontal line is still only going to pass through the graph of the function at one place for any given horizontal line. That means this is a one-to-one function. Okay, next look at one that is not one-to-one. Y is equal to x squared. Well, clearly there are lots of places we could place that horizontal line, and we could pass through the graph at more than one point. So x squared is not a one-to-one function. So graphically, very easy to determine. Don't get your wires crossed with the horizontal and the vertical line test, though. Remember, the vertical line test simply tells us if we have a function, whereas a horizontal line test tells us if we have a function, is that a one-to-one function? Okay, so let's find an inverse, which is denoted f to the negative 1 of x. And remember, in order for a function to be invertible, it has to be a one-to-one function. So this is the general process we follow to find the inverse of a function. We interchange the x and y values, and then we solve the function for y. You can also solve the function for x and then switch x and y at the end. Exactly the same method. You end up mathematically doing the same things, so whichever method makes you happier. By all means, if you want to solve first and then switch the variables, you can do that, or you can switch the variables first and then solve. Whatever makes you happiest. Okay, so first we're going to see, are these functions invertible, and if so, prove it. And we're going to first look graphically. And remember, invertible means one-to-one. So letter A, 4x squared plus 5. Well, there's a graph of that parabola. Clearly not invertible, not going to pass our horizontal line test. Okay, letter B here, the function f of x equals e to the x. Well, there's a graph of e to the x, and this is going to be invertible because it's one-to-one. Whenever we would draw our horizontal line in here, we would touch that graph only one place for each horizontal line. So it's one-to-one, hence it's invertible. Also, you can look on page 39 in your book. There are some pretty good diagrams there of one-to-one and invertible functions. Okay, next, a little bit more taxing of a task here. We're going to prove that a function is invertible algebraically. And to do that, that means when we compose the function with its inverse, it's exactly equal to what we would get if we were to compose the inverse of the function, and both of those things have to generate a value of x. So, are the following functions invertible? And if so, prove it algebraically. And those directions are pretty important. If it doesn't say prove it algebraically, you can graph it, check for one-to-one, and if it's one-to-one, it's invertible. Life is good and you move on. But when it says prove it algebraically, we're going to have to do the math. Okay, so job number one here is let's find a function for the inverse. So we're going to follow the method of we're going to solve this equation for x in terms of y. So if I take my equation here, y is equal to negative 2x plus 4, and I do some algebra on it, I'm going to subtract my 4 from each side, and then I'm going to divide out that negative 2 after I do all my simplification. In terms of x, that is equal to x is negative 1/2 y plus 2. Next, I'm going to switch the x and y variables, so I'm going to change that to be y is equal to negative 1/2 x plus 2. And now I'm going to do the math. I'm going to do f composed with the inverse. So or actually this one has f inverse composed with f first. No big deal, we have to do it both ways. So f inverse of f of x. Well, f of x is negative 2x plus 4. So we're going to put negative 2x plus 4 into our inverse function, which says to multiply by negative 1/2 and add 2. So negative 1/2 times our negative 2x plus 4, and then add the 2. Distribute that negative 1/2, we get x minus 2, and then plus 2, and x minus 2 plus 2 is simply just x. So f inverse composed of x gives us a value, f inverse composed with f of x gives us a value of x, which is what we're looking for to prove that it's invertible. But remember, it has to work both ways, so now we need to do f composed of f inverse. So now we're going to take our f inverse function, this negative 1/2 x plus 2, and we're going to run that through the f of x process. So we're going to multiply negative 2 times this negative 1/2 x plus 2, and then we're going to add the 4. So if we distribute this negative 2 through these parentheses, we're going to get x minus 4, and then we have the plus 4 here, so x minus 4 plus 4 gives us a value of x as well. So f inverse composed with f and f composed with f inverse are equal to each other and both equal x. So yes, that function, negative 2x plus 4, is invertible, and the inverse of that function is negative 1/2 x plus 2. Okay, letter B, f of x equals 1 over x to the 4th for a domain of x being greater than 0. Well, first we need to find an inverse function. So here they chose to solve for x first and then switch the variables. I'm going to do it the other way just to prove that either method works. So I'm going to take my y equals 1 over x to the 4th, and I'm going to solve this for, or I'm going to switch my variables first. I'm going to change this to x equals 1 over y to the 4th. And now I'm going to solve for y. So if x equals 1 over y to the 4th, if we do some algebra, we multiply each side by y to the 4th, and then we divide by x. That gives us y to the 4th is equal to 1 divided by x. And then to solve for y, I'm simply going to take the 4th root of each side. So that's going to give me my inverse function as y is equal to the 4th root of 1 over x. Okay, let's test out the math. Let's do our composites here and make sure that everything is okay. So f inverse of f of x. Well, here's f inverse. So I need to take the 4th root of 1 over the f of x function, and the f of x function is 1 over x to the 4th. So the 4th root of 1 over x to the 4th, simplifying under the radical first, 1 over x to the 4th is simply x to the 4th. So I'm really taking the 4th root of x to the 4th, and the 4th root of x to the 4th is x. Okay, let's do our second composition. Let's do f composed with f inverse. So I'm going to put the f inverse function, I'm going to put this 4th root of 1 over x into the f function, which says 1 over x to the 4th. So I have 1 over, here's my inverse function, to the 4th power. Well, when I have the 4th root of something raised to the 4th power, those cancel one another out, and I'm left with 1 over 1 over x. And then algebraically we simplify 1 over x is simply equal to x. So f inverse of f and f of f inverse are equal to each other, which are equal to x. So yes, 1 over x to the fourth with that domain of x being greater than 0 is invertible, and the inverse of that function is the fourth root of 1 over x. Okay, example 3 on page 40. This sort of puts our parametric graphs to use that we talked about just a little bit ago in section 1.4. So part A says graph the one-to-one function f of x equals x squared with the domain that x is greater than or equal to 0. This is super important because if we didn't restrict this domain, this would not be a one-to-one function. It's a parabola which is not one-to-one on its entire domain, but when we restrict its domain to be greater than or equal to 0, we now have a one-to-one function we can work with. So we're going to graph that function. We're going to graph its inverse, and we're going to graph the line y equals x. Okay, so here's how we graph parametrically this function f of x is equal to x squared. Simply, x equals t and y equals t squared. Pretty easy. When you want to graph the function, you just let x equal t and y equal that function you want to graph. The function we wanted to graph was x squared, so x is t, y is t squared. And this is maybe one of the coolest applications of parametric equations that I've seen. To simply find the inverse, we switch the x and y. So this time for the inverse function, we let x2 be the t squared function, and we let the y2 be the 2. And now these two parametric equation pairs are inverses of one another. And then to graph the line y is equal to x, which is how we sort of show that a function and its inverse are really what we say they are. All we have to do to graph that line of y equals x is we let both x and y equal t. So if we were to put all three of these things into our Inspire, here's a picture of what you will see on your graph screen. And by all means, go ahead and stop the video right now and enter those things if you would like to, just so you can see it happen right before your very eyes. And when you do that, you should get something that looks very similar to this. First of all, the blue line here, this is the first parametric pair when x is t and y is t squared. You can see that looks like the right half of our parabola, which comes from right here, x squared, for our domain of x is greater than 0. And then here in the red, these are our second pair of our parametric equations. That's when we do the inverse, and we let x be the t squared and y be the t. And sort of intuitively, you should know that the inverse of x squared is the square root of x, and you can see that indeed that is a graph of our square root function. And then lastly, the black line is the line y is equal to x, which we generated simply by letting x equal t and y equal t. And right there is graphically what we see when we graph a function and its inverse on the same graph. We can see that we have been mirrored around this line y equals x. Okay, part B of example 3 says express the inverse of f as a function of x. So this is parametrically how we express it, which is pretty easy. It's a pretty handy application of our parametric graphs. Part B asks us to express our inverse as a function of x. So what we're going to do is we're going to go through that process of determining an inverse. So if f of x equals x squared, that means y is equal to x squared. So solving for x, we're going to get that x is equal to the square root of y. And then swapping those variables, y is equal to the square root of x. So that means our inverse function of x squared, like we talked about a little bit earlier, the inverse of that is the square root of x.